Hello, welcome to Notes 5.06. Today, we're looking at dilations and scale factors, okay? Now, this is a nice little bridge into our next unit. Our unit 6 that'll start after our test next week is going to be on similar triangles or similar figures where we have one small triangle and a big triangle said to be similar to each other. So that's where we're moving into Unit 6. So this last topic for Unit 5 today is really just to kind of have our brains start thinking about dilations, and it does relate to our coordinate plane with the last few questions we'll do today. So to start off, dilations are not rigid motions. They are similarity transformation, which again, similarity is the unit we're going to be moving into, meaning the sides will have proportional measures. Today we're going to construct a couple dilations of a triangle, and we're going to examine them and graph in the coordinate plane. There are two important parts of a dilation. There's your scale factor, meaning how big or how small it's getting. So K is actually also used for scale factor. Scale factor could be by 2, so you could dilate by 2. You could dilate by 1/3 the size. So those scale factors are the measurements deciding if your shape is starting small and getting big, or reversing, starting big and getting small. Okay. So we have a scale factor, and we also have what's called the center of dilation. I know most of you have cell phones, and I'm going to show you here what I mean by that. So what I mean by center of dilation is on your cell phones, you guys know, here's my little guy, this is my little Owen. If you really wanted to take a peek at his face, you would kind of squeeze your fingers close to where you wanted to dilate your picture, and you'd make it bigger or smaller, okay? So that dilation is where I'm kind of placing my fingers on my picture. So when we talk center of dilation, it's where that picture kind of originated to get bigger or smaller. Okay. So given the diagram of triangle DEF, and it's dilated by a scale factor of 2 to get triangle D prime, E prime, F prime. We're going to use a straight edge to find the center of dilation. So the center of dilation, if you think about one of your art classes, is really your focus point. So what we do here, and again, I did grab a straight edge. If you have the side of your laptop to use or anything you want. D to D prime, we're going to connect just with a line. Okay, so again, I just kind of lined my straight edge up to a point D and its prime piece. Then I'm going to connect F prime here to point F. And again, I'm lining it up best I can. And I'm going to just kind of draw a little mark there. I'm going to come down, do the same with E and E prime. Now I have some error here. See how I didn't quite go through F? But as you connect all three pieces, those should make a nice little point over here. So again, I have a little error with my F. I might just erase that one. I make mistakes on these just like you may. Line that up a little bit better. There we go. Now we're going to go through F prime and through F. And there we hit a better point of intersection. Okay. So when you connect each point, so we connected D to D prime, kind of extended outside our picture, that's going to be our. So again, this is going to be our center of our dilation. Also, and I did just pause to look it up, it's called a vanishing point. If you're thinking about an art class you might have taken, where all three of those pieces kind of connect back to the center of dilation. And we're going to call that C. Yeah, so that's just constructing where the center of dilation is. And then from that point, that triangle extended to become twice its size. So we had DEF as the small, D prime, E prime, F prime was the larger. Exercise 2. We kind of extend into the coordinate grid. Triangle A prime, B prime, C prime is the image of triangle ABC after a dilation. So in this case, the shape is getting bigger or smaller. Let's take a look. We start with ABC is a bigger triangle, and it becomes a smaller triangle. So we're going to use a straight edge to find the center of dilation, and we're going to find the scale factor of our dilation. So just like we did on the first example, we're going to connect each point to its prime. So C to C prime, we're going to connect together. B connected to B prime, and A and A prime happen to be above each other, so it's kind of easy. Where all three of those pieces connected to this center of dilation here, we're going to call that maybe X this time. The C is already an ordered pair. Okay. So that point X, if we read it from the origin, is 1, 2, 3, 4, 5 over 2 up. So the center of dilation is an ordered pair in our case for the coordinate plane question, and it's at 5, 2. Scale factor. Scale factor is the new piece. Now, the first question they told you was dilated by a scale factor of 2, where if I were to measure maybe E to F here, it's about 1 1/4 inches. Okay. E prime F prime should be about double that measure, about 2 1/2 inches. Okay. And again, that's an approximation. So scale factor down here, we need to take a side of the new over a side of the old. Now, again, it started big, it's getting smaller, okay? So a side of the new is actually going to be this distance here, X to A prime. So it's how far from your center of dilation each ordered pair ends up being. So the easiest way I found to kind of explain this is from X to A prime is 1, 2, 3 boxes away. And again, we're looking at this as a ratio, okay? And X to A is the old. X to A is a segment of the old. That is 1, 2, 3, 4, 5, 6 boxes. So if X to A prime is 3 boxes, but it used to be 6 boxes away, that means it's gotten half the space closer, or half the distance closer. So it came in by 3 boxes there. Same thing if we were to look at C to C prime and C prime to X and C to X. From C to X is 1, 2, 3, 4, 5, 6, 7, 8 spaces away, but C prime to X is only 4 spaces away. So if it was 8 spots away, now it's jumped half that distance to be 4 spots away. So it did become smaller by a half. So again, our scale factor little formula is a side of the new over a side of the old. So first question, I told you the scale factor, we found the center of dilation. Second diagram, we had an original and a smaller. We found the center of dilation and the scale factor. Exercise 3 here talks about segments. This might make some more sense for some of us. A dilation centered at O, so here's our starting point, produces image A prime, way out here, as shown below. So from A to O, it's 9 inches away. Now, A to O prime is what we're looking for. Is how far is it from A to O prime if the scale factor is by 3. So A to O is 1 section away, 2 sections. Now it's 3 sections out. Well, if each section is 9 inches, O to A prime is 27 inches away. So we just multiplied in that case, 9 3 times over, understanding the idea of scale factor. Again, that kind of related back to what we just did with the directed line segment questions. Moving on to number 4. Given triangle RST graph below, dilate given the scale factor and center of dilation. So here we have triangle RST. Our scale factor is telling us we want it to become twice as big, times 2, and the center is point T. So that being our center of dilation, we're going to kind of pinch there and make that triangle bigger so that T kind of stays actually in its location. So how we're going to do this is we're going to find the slope from T to S, the rise and the run, and repeat that so it becomes a second time over. So it scale factors it and makes that length twice as big. So that's kind of like our scale factor we did over here. This was 6 spots away. We made it half the measure in, which became 3 spots away. So here we're making it bigger. So our slope from T to S is down to 1, 2, 3, 4 over. That would really be the length of TS, right? As a hypotenuse. We're going to repeat that one more time. Down to 1, 2, 3, 4. That's going to find you S prime. It's right here. We're going to do the same process from T to R. So we're going to find the slope from T to S, and then we repeated it. Same thing from T to R, and we're going to repeat that. So from T to R, we go 1, 2, 3, 4, 5 down, 2 over. 1, 2, 3, 4, 5 down, 2 over. Becomes R prime. And now if I connect that shape, we're going to see that T to R prime, I10 to S, and S back to T became twice as big. So by repeating the slope, you made really S the middle point on that whole segment from T to S prime. And same thing in the opposite direction. So again, we just repeat the slope. So here we took a graphed figure and we dilated it in the coordinate plane. Now we could list the coordinates. So S prime is now a new location. R prime is at a new location. So we have 1 and 1, 2, 3, 4 over 1 up 4. R is -3, -2, if they happen to ask you for it. Question number 5. Determine the scale factor between triangle ABC and A prime, B prime, C prime. So that's our larger one. So I'm going to label that A prime. C prime is up top because C is the top point, and B prime happens to be over here. So again, to find your scale factor, and it's written down here for us, we take a side of the new over the side of the original. So your scale factor, you always take the new over the old. So we're going to find A prime, B prime. Why did I pick that one? Because it's horizontal. I can just count those boxes. It's a nice, easy length to be finding. Over the old segment would have been the OG, AB. So A prime to B prime, well, that's 10 over plus 4 more is going to be 14 across. And A to B is 1, 2, 3, 4, 5, 6, 7 across. So again, A prime to B prime is 14 across. AB was 7 across. Well, 14 divided by 7 is 2. So can we agree that our small triangle, ABC, dilated twice as large to become the new one, A prime, C prime, B prime. 2. So our scale factor is 2. And sketch the center of dilation. So to find that center of dilation, again, we use our straight edge and we connect A to A prime, just go straight down. Now C to C prime, and kind of come down at a diagonal, and B to B prime, again, a little bit off here. I think it was my C and C prime pieces. So let's kind of go for the middle piece here. Maybe -4, -10 would be our center of dilation. I'm going to practice kind of doing that in a few minutes. So a little practice with the scale factor. Remember, dilations will always have a center of dilation and a scale factor. To determine your scale factor, we do a new over the original. So from these two shapes, we have to decide what is the original shape and what is the new shape. So reading here, what is the scale factor from A? So from is your old, that's where you're starting, to make B is the new. So this is your new shape, this is your old shape. So again, from A, from the old to the new. So you're going to take a side of the new, maybe 4.5 or 5, it really doesn't matter which shape or which measure. So I'm going to go with the top measure here. 4.5 goes in the numerator, new numerator, and that corresponds to the old of 9. Well, 4.5 divided by 9 should be 1/2. So if this is the old shape and the new shape, did that get a half the size from the old to the new? It did. So again, that's where you take the new over the old. What's the scale factor from B to become A? Now we can decide that that became smaller. Okay? So again, we need a side of the new being A over a side of the old. So we're going to have 4 over its corresponding piece 6. It's going to become 2/3 the size. And that works for any set of sides. If I took 5 over the 7.5, I'm going to get a ratio of 2/3 as well. So 4 divided by 6 gives us 0.6 repeating. So, and that's this side compared to that side. Any other measures work as well. This 3.5 divided by your 5.25 gives you the same ratio. So it doesn't matter which set of parts you use. Again, we use the side of the new over a side of the old. So that's where my 4 to 6 or 2/3 became. Dilating a segment in the coordinate plane. So now those dilations, again, we have this sketched one here for you. This triangle was sketched in the coordinate plane for us. We had the center of dilation and we got bigger from there. This next question is related to a dilation where you're on the line with the center of dilation or where your center of dilation is off the line. Okay, and that we're also going to extend for segments and infinite lines. So thinking y equals mx plus b. So if your center of dilation is on the line, so sketch the dilation of segment RS. So we're having a start and an end. After a dilation of scale factor 2, centered at O. Label the points R prime and S prime. So this segment here, RS, is dilating in relation to O. So if I kind of pinched at O and made this bigger, twice as big, right? Scale factor of 2. R prime is over here, and S prime is going to be its same distance from O. So that R prime S prime is 2 times as big as R to S was. So again, I moved R, its same measurement out. I moved S, its same measurement out. Okay. so that RS, twice RS, I should say, equals R prime S prime. 2 times that measurement equals the new measurement, because it got bigger. In the coordinate plane, we have that same kind of idea happening. Here we have triangle ABC, and again, that center of dilation, we hold that middle of the segment still, and we kind of bump out the other pieces. So A doubled its measure away, B doubled its measure away, and C kind of from that center of dilation doubled its distance away. So we're going to be looking at those centers of dilations in the coordinate plane as well. But that's when the point is on a center of dilation. Your center of dilation is on your segment. My apologies. Center of dilation off your segment. Sketch the dilation of CD after dilation scale factor 2 at O. Label the points C prime and O prime. So from here, we have a line sketched, CD on the line. O is a point off the line. Here, O is a point on the line. And we kind of just went twice the distance away. In this case, we kind of have to go along a diagonal. So O to C, we want to dilate C twice as far. And again, that direction is important because we're kind of going a little northeast here. We're going to go the same distance away to find C prime. Same idea along this, it's called a vector. V-E-C-T-O-R. And you do more of vectors in physics class. But a vector is a segment with direction. Okay? So it's a segment that has direction. So this vector would come maybe as like a southeast version if we're thinking about northeast, southwest. Okay? So this is going to kind of come southeast and go the same distance out. So again, I'm kind of just sketching here, and D prime is down there. So when we sketch this new line, C prime, D prime, so that this measurement and this measurement were about the same, I rolled it off, that measure to here and this measure to here were about the same, we get 2 new points such that C to D is parallel to the new segment, or the new line, C prime, D prime. Okay? That these segments run parallel to each other. That's a key fact, okay? That the slope from C to D will equal the slope from C prime to D prime. So looking in my coordinate plane here, these 2 segments run parallel. The rise and run would be equivalent fractions. But BC is dilated a half the size to become B prime, C prime. Now, if I find the center of dilation by connecting C and C prime, B and B prime, we actually form 2 triangles. Okay? I'm going to call this point O. So we have the little triangle, which is O, B prime, C prime. We also have the larger triangle, which is O, B, C. So those 2 triangles are going to be similar in their sizes. And we're going to be coming back into this in our next unit. But again, the center of dilation would be O in this case. And we could prove, again, BC would be running parallel to B prime, C prime after it's dilated. And lengths, okay? Again, the whole measure was 4 units away, B to O. The new distance to the center of dilation is 2 units away. So remember, we have new over old. Side of the new is to B prime, because that's your image, that's your new piece, is 2. The old measurement was 4 units away. So we can conclude that BC got half its measure as it dilated, as it snuck in. So that idea of being parallel is important for this type of regions question. So looking down at the bottom of the page, trapezoid ABCD is dilated about the origin by a scale factor of a half, creating trapezoid A prime, B prime, C prime, D prime. So this picture would kind of fall a little bit closer from each corner in to get a new one half that size. So almost think of it as a donut, okay? So it shrunk in just around that origin. So again, those four sides, we sunk in, centered at the origin, okay? Which of the following statements is true about AB and A prime, B prime? So AB is a line, A prime, B prime would be this one. What appears true about those two segments? The lines intersect and have negative slopes. Well, they do come down our page, so it does have a negative slope, but these lines are definitely not intersecting. Even if I extended them, those won't intersect. So it's not the first choice. The lines are perpendicular and have negative reciprocal slopes. Those aren't perpendicular. The lines are parallel and have equal slopes. Yes. So a little key fact to this is that a dilation preserves parallel sides. Okay? So it keeps things parallel as it gets bigger or as it gets smaller. So those questions kind of lead us right over and into coordinate plane application. So here, I'm actually only going to do examples 1 and 2 for now. I'm going to leave off example 3 for timing right now, and we'll come back to this next week. But example 1, we're dilating the line. So a line, remember, is infinite with arrows at either end. 3x plus y equals 10 by a scale factor of 2 centered at the point 2, 4. So you have to graph this. So I've already graphed this point 2, 4 for myself. But this line here I need to graph. So 3x plus y equals 10. I can't graph that until I get the y standing alone. So remember, we need to move your y value, or I'm sorry, move our x value over. It reads y equals negative 3x plus 10. So our slope is negative 3 over 1, and our y-intercept is 10. So again, we're going to dilate this line by a scale factor of 2 centered at the point 2, 4. Now, there's 2 steps here that I kind of skipped over reading for this purpose. Step 1 is to check if the point is on the line. Sub in x and y. I know a lot of you are pretty visual. I'm going to graph this line. So now that we have this y equals negative 3 half x plus 10, we know our y-intercept is 10, and I'll tell you it's a 10 by 10 grid. And when you rise 3, run 1, rise 3, run 1. Well, I've already hit that ordered pair 2, 4 that we're supposed to be graphing. Down 3 over 1. So that point, 2, 4, is on this line that is already infinite. So if my center of dilation is already on a line that is infinite, I can't move that line. This equation is not going to change. So when you have to dilate a line by a scale factor of 2 centered at a point 2, 4, and that point happens to be on the line, you can't dilate something that's infinite. So we're going to say here, this line will not change. So the equation is going to read y equals negative 3x plus 10. That point is on the line. And if I put in that ordered pair, 2 in for the x and 4 in for the y, 3 times 2 plus 4 is 10. So that just kind of confirms that this point does satisfy that equation to be on the line. Exercise 2. The line represented by the equation 4x plus 2y equals 8 is transformed by a dilation of 3 centered at the origin. Write the equation of the line's image. So the image is the new line. So what it's looking for, write the equation, is like a y equals mx plus b, is what our final answer should look like here. So the line represented by this equation, 4x plus 2y equals 8. So a couple key pieces. We have an equation that we're starting with, 4x plus 2y equals 8. It says the dilation scale factor is 3. And our center of dilation is the origin, which we know to be at 0, 0. So I'm going to kind of color in our center of dilation. Okay. So again, there's a couple key pieces given. Typically, the questions we were looking at before were triangles. And that triangle got dilated from a center of dilation with a certain scale factor. Here, we're dilating a line, an infinite line. Now, first off, I can't graph that line without getting y alone. So we're going to subtract 4x from both sides. 2y equals negative 4x plus 8. So divide through by a 2. Y equals negative 2x plus 4. So this is our original line. I'm going to graph that. Y equals 2x, negative 2x plus 4. So plus 4 on the y-axis, down 2 to the right 1, down 2 to the right 1, down 2 to the right 1. It does give me a negative slope. So something important about the new line, scale factor of 3, means that this line has to get 3 times farther away than the original. So if my segment is on this little post-it note, okay, that line isn't becoming longer or shorter. Its distance from the origin is getting 3 times farther away. Okay. So again, think of my post-it note as this line. We're moving it 1, 2, 3 times farther away. Okay. Now this little triangle formed here is important. So do you see the triangle formed by this ordered pair, this one, and the origin? Oops, there it goes. Okay. That triangle is going to be our key piece. It's 4 boxes up, right? 1, 2, 3, 4. And 2 boxes across. That triangle we're going to make 3 times farther away. So if it's 4 boxes over now, 1, 2, 3, 4 more, that ordered pair along, if this is 2 over, we go 2 more. That's twice as far away, isn't it? In both directions here and here. Well, we want to go 3 times farther. So that y-intercept was a 4, right? This one would be 8 to be twice as far. So we're going to multiply it 3 times over to get a distance, total distance from the origin to be 12 boxes away. So our y-intercept is the key piece here. So that y-intercept is now going to be 12. And the x-intercept, so we went 1, 2, 2 more, 3 boxes over is 6. So if I sketch the new line up 12 and over to here. This pink line is now 3 times farther from that origin. So the distance here, here, and here would be 3 times farther away if you're kind of going at a diagonal. Okay? So the only thing that we changed, the slope of the line didn't change. These lines, remember, will always run parallel. So this is step 2 up here. If the center of dilation is the origin, and that origin is not on the line, keep the slope, which was our -2, and dilate the y-intercept. Okay. So our new equation, y equals mx plus b, is what we were thinking. We need to decide the slope and the y-intercept. Well, the slope is going to stay the same because the lines have to be parallel. So I'm going to use my -2x, stays the same here. But my y-intercept, at 4, now became 12 pieces away. So the y-intercept becomes plus 12. So that's how we dilate lines. Now, do I expect you to understand this by doing really just 2 of these? No, we're going to come back to this idea in Unit 6. We just needed to kind of introduce it now so it's a little bit easier to understand later. What I'd like you to be doing now is try what you can on classwork 5.06, right? Write a ratio of the sides from the scale factor. So remember, ratio of your sides is your scale factor. I want a side of the new over a side of the old. So I want a ratio, a fraction, a numerator denominator here. Read question number 2, try to make sense of it. It may help to connect, to kind of form the triangles there. And again, those are similar triangles. We're going to be doing more in Unit 6. See what makes sense for number 3. It's a multiple choice question. Looking over here, number 4 says, Alex says this line, 4x plus 3y equals 24, dilated by a scale factor 2 centered at 3, 4, is this new equation? Is Alex correct? Okay. Explain why. Now, use of the grid, I would not say is optional. So I want you to graph the new, graph your center of dilation, this is the original equation. That's your center of dilation. This is your new line. I would graph those 3 pieces. Decide if this Alex is correct or not on that idea. If it was a scale factor 2 and centered at that dilation. Okay, so again, if you have a line, you have a center of dilation. If this is your old line and you want your new line to be twice as far away, your new line should kind of run parallel to the old. That would be the case. This diagram would be the case for a true case. If these 2 lines, the new and the old, are parallel, and the new one is twice as far away. See what you can do, make sense of the topic. Talk to you soon.